Hello learners. Till now in the video lectures we have seen how to calculate we have derived an expression for bending stress for curved beams. The final expression for bending stress in curved beams goes like m by m divided by a by r in the whole bracket 1 plus r square by h square into y divided by r plus y. So in that equation m is nothing but the bending moment applied in the B. Here is the cross section of the B. R is the initial radius of curvature. R square, h square is a constant for a particular cross section. In the last lectures, we seen how to calculate h square for various cross sections. Y is nothing but the distance where you need the bending stress from the centroidal section. So in this lecture, we will be seeing some problems on curved beams. So the important factor in curved beams is in curved beams, wherever you apply the load, it will not pass through the centroidal section. So once the load is not passing through the centroidal section, you will be having two stresses. One is direct stress and another one is bending stress. It is given like in all the curved beam members, the line of action, the load does not pass through the centroid of the section, for which the stress is to be found. Due to this, the total stress over the section will be algebraic sum of direct stress and bending stress. So the total stress is nothing but direct stress plus bending stress. So how will you calculate the direct stress? It's very simple. It's how you calculate stress in an axial member. Load divided by cross-sectional area. P divided by A. How do you calculate bending stress? To calculate bending stress for curved beams, we know the expression for bending stress. So upon adding these two figures, you will be getting a total stress in the cross section. So in almost all the curved beam problems, we have to find two stresses. One due to direct stress, which is nothing but P by A, and one due to bending stress. We know the expression to calculate bending stress for curved beams. So we will go into the first problem. So the problem is find the resultant stress at points A and B as shown in the figure 5.19. It carries a load of 2 kilonewton. So even though it is a curved beam, once you cut this section, it will be rectangular. The first thing you have to note down is the cross section will be rectangular. Even though it is a curved beam, you cut a portion AB in the curved beam, you will get a rectangular cross section. Here it is given the dimensions of the rectangular cross section is 50 mm by 20 mm. 50 mm depth, 20 mm breadth. And this 2 kilonewton load, it is acting like it is going to pull the hanger apart. So here we are assuming the moment here it will be created is 2 kilonewton into 150 mm. We have to go up to the perpendicular distance, we have to go up to the centroid of the section. So it's 150 mm plus 50 mm. So total distance is 200 mm. So the moment here is 2 kilonewton into 200 mm. Here you have to assume whether it is a positive moment or negative moment. The load which is acted like it is going to pull the ends apart, we are taking that moment as negative. When the farther two ends are closed, we are taking it as positive moment. When the farther ends, the end part of the hook or crane, when it is pulled apart, that moment we are taking it as negative. Since this 2 kilonewton into 200 mm moment is pulling the ends apart, we are taking this moment 2 into 200, it will be coming 400 kilonewton mm moment as negative. And also the distance y. The maximum stresses will be induced at the extreme points. That means the points A and B. The outside part A, we are taking it as plus 25 mm. The inside part B, we are taking it as minus 25 mm. So these two things we have to be very careful in the problem. So the moments which are trying to pull the end parts apart, we are taking it as negative, and the centroid, the distance y, the outer part A, we are taking it as plus 25, and the inner part we are taking it as minus 25. So here it's given with B is 20 mm and depth D is 50 mm. Load is 2 km, means 2 into 2, 10 power 3 Newton. Radius of curvature is 50 mm. So we have to find resultant stress at point A and B. So area of cross section, we know B into D is 20 by 20 cross 50,000 mm square. Bending moment is load into distance. As I told, it's 2 into 10 power 3 Newton into 150 plus 50 mm. It's 400 into 10 power 3 Newton per mm. Since the force is pulling the ends apart, we are taking this moment as negative moment, minus 400 into 10 power 3 Newton per mm. So before calculating the bending stress, you have to calculate h square for that section. Here the section is rectangular section. For calculating h square for rectangular section, the expression is r cubed by d into ln of 2r plus d divided by 2r minus d minus r square. You know all these parts. We know initial radius of curvature is given 50 mm. Total depth of the section is also given as 50 mm. So upon substituting that and calculating that, we find that h square is 246.5 mm square. So h square is nothing but 246.5 mm square. As I told you earlier, there will be two stresses acting upon this curved beam. One is direct stress. We can calculate by the formula P divided by A. So here the force is 2 into 10 power 3 Newton. The area is, we calculated 1000 mm square. So we are getting direct stress as 2 Newton per mm square. It will be of tensile nature. It will be of tensile nature. And the second stress is bending stress. So for B lies in the inside part of the structure. So here we are taking it as minus. So B lies inside. We are taking as minus. So upon substituting that, we have moment minus 410 power 3. Area we know 1000 mm square. Radius of curvature is 50 mm. So similarly, radius is 50. H square we have calculated. We have calculated as 246.5. So here you have to substitute it as 246.5. You should not square it. Here it is given in the wrong manner. So h square itself we have calculated as 246.5. So we just have to substitute 246.5, not square it. So y is, we are seeing at the extreme distance. B lies in the inside part of the section. So it's minus 25. So y instead of y we are substituting that in numerator minus, we have taken it outward, taken it outside the bracket, and the denominator part minus 25. Upon calculating that, we getting the bending stress at the point B due to the moment as 73.128 Newton per mm square. Similarly, we are going to calculate bending stress at point A. So A lies on the outside part. So here we are taking it as plus y, 25 mm. So upon substituting again all these things, we are getting minus 35 Newton per mm square. So the resultant stress at point A is direct stress, it's tensile 2, and bending stress at point A is minus 35. So minus 35, upon we are getting it minus 33 Newton per mm square, which is given as 33 Newton per mm square compressive. So minus, here they are saying it as compressive. So resultant stress at tensile point B. So 2 plus bending stress at point B due to moment is 73.128. Upon adding, you will be getting 75.128 Newton per mm square, which is tensile in nature. So when you see the figure, when 2 kilonewton is acting upon this hook, the point B, you can physically see the point B, it is going to stretch out. The point B is going to stretch out. So at that point B will be of tensile nature, at the A it will be compressed. So at point A there will be compressive stress, at point B there will be tensile stress. We will see what we got. So similarly at point A we got compressive stress, and point B we got tensile stress. So this is very simple problem. Once you know the formulas and apply it clearly, you will be getting the answers. We will look at in the second problem. Here in figure 5.20 shows a crane hook lifting a load of 200 kN. Determine the stresses at the inside and outside fibers of the hook on a horizontal diameter passing through the center of curvature. Here the cross section it is given as trapezoid. Here the cross section it is given as trapezoid. So for calculating h square, you will be applying the h square for trapezoidal section. So here the small width is 50 mm, larger width is 150 mm. So total depth is 200 mm. The radius of curvature is 100 mm. The load is 200 kilonewton. So this load also pulling the ends apart. So here also the moment is negative, and A it's plus. A you have to put y as plus y, and B you have to put it as minus y. Since it's a trapezoidal section, it will not be same. So you will be having small d1 and capital D1. Sorry, D1 and D2. A is plus D1 and B is minus D2. Okay, A lies in the outside, so it is plus. B lies in the inside, so it is minus. And the moment is also a negative one. So width of the section is B, capital B is 150 mm and the small b is 50 mm. Depth of the section is 200 mm. Load is 200 kN. We are going to find the stress. Area of cross section, area of trapezoidal section is capital B plus B divided by 2 into D. We are getting as 2000 mm square. Now we are finding D1, distance of breadth from centroidal distance. So D1 is D by 3 B plus 2B divided by B plus B. You are getting 83.33 mm. For calculating D2, you can minus D1 from D. So it is 200 minus 83.33. It is 116.67 mm. So radius of curvature you have to add. Here you have to see. So the radius of curvature is not 100 mm. You have to add distance of D1 to the 100 mm to get the radius of curvature. It is 183.33 mm. So bending moment is load into distance. As I told, the load applied in such a manner that it's going to pull the farther end apart. So it's minus 200 into 10 power 3. The radius of curvature you are going to add, it's 183.33. So the total moment is coming as minus 36.66 into 10 power 6 Newton per mm. So now we are calculating h square for triple section. This is the large formula, but luckily we know all the terms in this. The radius of curvature we have calculated is 183.33. Area of trapezoidal section we know. Small b we know. Small b is nothing but 50 mm. Radius is 183.33 again. And D2, D1 we have find out. D1 is 83.33. D2 is 116.67 mm. So upon substituting similar terms in this large expression, luckily if you do it correct, you will be getting h square as 3238.96 mm square. 3238.96 mm square. So in a curved waves there will be two types of stresses acting. One is direct stress and another one is bending stress. So direct stress P by A. P we know 200 kN, 200, and area is 20,000 mm square. Upon calculating, we are getting direct stresses 10 Newton per mm square. These direct stresses usually will be of tensile nature. Then bending stress due to moment at point A. Since point A lies outside, the term D2 will be taken as positive. Here you can see h square. Instead of h square, they just substituted 3238.96. Not as they done wrongly in the previous sum, it is not taken as 3238.96 whole square. So upon substituting all these terms, we know all these terms. This is just calculation, easy calculation. You are getting bending stress at point A is 50 Newton per mm square compressive. You are getting minus 50 Newton per mm square. It means you are getting 50 Newton per mm square compressive at the point. Similarly for bending stress due to moment at B. These two things you have to be very careful. Since B lies in the inside, instead of putting D1, you have to put minus D1. And substituting all those terms, you will be getting tensile stress at the point BS, means bending stress at the point BS 76 Newton per mm square, which comes as tensile. So you add direct stress and bending stress at points A and B, you will be getting the total resultant stress at point A is 40 Newton per mm square and the resultant stress at point B is 86 Newton per mm square, whereas A it is compressive and at B it is tensile in nature. So here on a brief note, the problem solving is very easy compared to the derivation part, but here there are two important points you have to notice. But first is whether the moment is positive or negative. When the load applied in such a manner that it pulls the farther ends apart, we are taking that moment as negative. That you have to be very careful. And also whether it is plus y or minus y. In the rectangular section it's very easy. It's a symmetrical section, so you will be getting y by 2 and y by 2. But in trapezoidal section it will be like D1 and D2. If the point where you are calculating the bending stress lies in the outside, you are taking it as plus, whereas if you calculate the bending stress at a point lies in the inside of the curve, you are taking it as negative. If you consider these 2 points, these problems are very easy and almost all the time it is asked in the semester question. Thank you.